So hello everyone and welcome to our last edition of the extremal and probabilistic webinar this year, so in 2020. Before we start with the seminar itself, let me go through the usual technical stuff. This seminar is being recorded, so please bear that in mind in case you ask questions. It will then appear on YouTube and on our webpage. If you do have any question, then just unmute yourself and ask it. There will be then opportunities to ask questions at the end, and we usually split it into a recorded part and a bit less formal unrecorded part. And so now it's my great pleasure to introduce Nati Linial from the Hebrew University. And Nati will talk about geodesic geometry on graphs. So Nati, please.
Thank you very much. Very glad to be here. Although I'm at home, but at least virtually. I'm now in many different places, visiting many different homes and offices and so on and so forth. So this is joint work with my student Daniel Cizma. In fact, this is more or less Daniel's master thesis. So today he presented it this morning in our combinatoric seminar, and with this he completed the requirements for his master's degree. And I'm very happy to echo it and present it myself. So what is the story? You know, I thought about this, and it's actually very interesting, you know, the things that Daniel is allowed to say, and I think the things that I'm allowed to say. So I think perhaps I have more freedom than Daniel. I've been very, very interested for a very long time. This has been a main thing for me in the connections or the geometric perspective on combinatorics and particularly on graphs. And really, if I want to be as bold as I can be, and I like to be bold about these things, the message that the message that you won't see in the slides, but I want to spell it out, is that really, I don't know, many areas of geometry, differential geometry, if you wish, can and should be developed on graphs. I mean, the fact that historically we've been doing this on manifolds and surfaces and so on and so forth shouldn't be a problem. And graphs offer you a lot of options that geometric things like manifolds and so on do not allow you. In particular, one huge advantage of working with graphs is that we have excellent models for random objects. And this is almost impossible to imitate in the continuous world. And so this offers a lot of new options, very fascinating. And so this is really the underlying theme. This is what we are trying to do now, to develop a theory of on graph, a geometric theory on graph that is supposed to be the discrete analog of geodesic geometry. Okay. Okay. Okay, so a good place to start, of course, the concept of tying together combinatorics and geometry or graphs and geometry is by no means new. Even this citation is far from being the first one. I mean, you can probably go as far back as Euler if you want to talk about this. But here is a very interesting concept, which I must say, you know, I've been doing graph theory for many years, and I learned about this only while working on this subject. So Øystein Ore was a Danish mathematician working in graph theory, in group theory, a very prolific mathematician. And he came up with the following nice definition. So he defined the graph to be geodetic. By the way, my geometry friends say that the right word should have been uniquely geodetic, but let's leave this aside. If it has the following property, between any two vertices, there is a unique shortest path. There is a unique geodesic. So do we know examples of graphs like this? Yes, trees, but that's a triviality because in trees, there is really only one path connecting any two vertices. Complete graphs, again, not very interesting. Odd cycles, slightly more interesting. Petersen's graph, I'll come back to this. If you don't see this right away, then we will go over this and you'll see this momentarily. In fact, any Moore graph, any graph where the diameter times 2 plus 1 is the girth, but we know that there are only, except for odd cycles, there are only finitely many such graphs. So there are additional examples, but understanding this thing in general is far from, I mean, it's still a mystery. So Ore presented this problem, which I think is a beautiful question. And we are still very far from having a satisfactory answer to Ore's question. So how to characterize such graphs? But let's let some very basic things about that graph. So if you have a geodetic graph, and if you're looking at the collection P of all the geodesics in this graph, then here are two very, very simple properties that the system of paths has. Between every two vertices, there is a unique path, U and V, so there's a path that we denoted by PUV. And it has the following consistency property, that if you take any of the path in your collection and you go through the vertices U and V, then the segment in which you could go along this path between U and V is PUV. That's a consistency condition. And so we abstract this and we say that a collection of paths in a graph that has these two properties, we call such a thing a consistent path system. This will play a major role in what we're discussing. Okay, so I'm almost able to state the main question that we're discussing. So now we have a graph, we have a consistent path system. We will see examples, and there is a very simple way to generate such things. If you have a length to the edges, let's not worry for a moment what happens if there is equality, just to understand that. Then this immediately induces such a system where PUV is just the shortest by weights path connecting U and V. This obviously has these two properties. And now we ask the reverse question. I give you, I think of things combinatorially. I give you a path system that is consistent, satisfies this consistency condition. So in certain graphs, in certain situations, this can be created by a metric, perhaps not always. And so the definition is a graph is called metrizable. And so make sure that you're with me, because that's the main, you really need to understand this definition, because this is what we're going to be talking about. A graph is metrizable if every consistent path system comes from a metric. For every consistent path system, you can assign length to the edges such that PUV is a shortest path between U and V. So first question is, are we talking about something, I mean, is there such a thing? So is it, are all graphs metrizable, or all graphs non-metrizable? So we start with a nice simple example, which is actually the first one that Daniel and I found. So the Petersen graph is non-metrizable. Okay, so let me say a word or two about Petersen graph. Petersen graph is a Moore graph. It has diameter 2 and girth 5, which means any two vertices, either they're adjacent or they're at distance 2, and then there is a unique path of length 2 connecting them. Okay, so what we do here is, so I need, again, what does it mean? What do I mean when I say that the graph is non-metrizable? This means there is a consistent path system that doesn't come from edge length. Okay, what's my path system? So first I have to show you a path system and then convince you that it cannot come from some system of edge length. My path system is this. Most pairs are connected the standard way. They're neighbors, take the edge between them. They're non-neighbors, take the unique path of length 2 connecting them. But there are 5 pairs for which my definition is different. And these 5 pairs are illustrated in this covering of the edges of the Petersen graph. For example, to go from vertex 2 to vertex 8, I follow the red path. I go from 2 to 1 to 6 to 8. Okay, or I follow the yellow brick path from 6 to 9 to 4 to 5. So consistency is very simple, because this is just a path of length 3 and all the standard path of length 1 and 2. So that this is consistent is very simple. So next, I want to convince you that this doesn't come from any edge weights, okay? So that's, in fact, if you think about it, it's a linear program. Take, for example, the first inequality that appears here. It compares the possibility of going from 2 to 8 the way we dictated it along the red path with what you would normally do, take the 2 steps, 2 hops path between them. So we say you go from 2 to 8 by going from 2 to 1, from 1 to 6, and from 6 to 8. And what you would normally do is you go from 2 to 3 and from 3 to 8. So there is such an inequality. Now add up all these inequalities, and what you conclude is that the pentagram in the middle, all these edges have weight 0, and we're assuming that edges have positive weights. So I showed you a non-metrizable graph. So non-metrizable graphs exist. Okay, let me jump a lot ahead of myself and say this. So what I'm saying now is non-precise mathematically, but it still carries the principle that you can show non-metrizability by picking up a path system and solving a linear program. That remains true, and this is a universal method. Okay, so which means in principle we have a technology to prove non-metrizability. What's hard in this technology is to guess the clever path system that's consistent and still would fail the linear program. But once you have such a system, such a collection of paths, showing that it's non-metrizable is relatively easy. You just plug it into your linear program solver and you know the answer. What turns out to be practically much harder is to prove metrizability. Now, I'm already telling you stuff that will appear at the very end. When we started thinking about this, I'm also a computer scientist, so I was ready to bet that deciding metrizability is an NP hard question. Turns out I was wrong, and it's in fact in P. But as some of you who have done computer science may know, being in P and being something that we can really solve well, there's a big gap between them, and we will see this. Okay, so here is the very short version of what we have discovered. 3 things. Metrizability is very rare. So I will be quite precise about this, but if you walk in the street and a graph falls on you, you're most likely, you should guess that it's a non-metrizable graph. Okay, if you encounter a random graph, whatever, you'll see. And you could then, okay, perhaps you could jump to the opposite conclusion. All of the graphs are non-metrizable. No, there are infinitely many interesting and non-trivial examples of metrizable graphs. And finally, in fact, the third one I already told you that it's polynomial time decidable whether a given graph is metrizable or not. But I emphasize, while it is that's a completely kosher mathematical statement, but as human beings, we don't really understand it. And we will have very simple examples of graphs whose status we still don't know to this date, although Daniel and I have worked quite hard. So that will be at the very end. How to think about this? We have to create a little, let me say one more thing about this paper. It's a long paper, it's a 40-page paper. And while I'm very happy with these results, and I think we've discovered some very interesting material here, I have to admit that this paper will not win any beauty contest. The proofs are long and technical, not very pretty, unfortunately. I wish I could show you some very elegant proofs and so on. There is one proof that is shorter and elegant, which I will more or less describe to you. But unfortunately, and this is, I think, just because we are only beginning, we still don't understand. So we've done what we could, actually, more precisely. Daniel did, he did, I think, all the bulk of the hard work. The consequences, I think, I'm very satisfied with, but in terms of beauty of the proofs, I cannot say that. Okay, So what are the tools? Yeah, we need some very basic tools in order to deal with this question. A path system, you understand. We're only talking about connected graphs, and consistency you also understand, right? Every subpath of one of the paths in your system should be the chosen path. There is something related to it, which seems a little surprising in the beginning, which is a tree system. So a tree system, like you have a path system, every two vertices are connected by a unique chosen path. Here you have a collection of spanning trees. For every vertex, there is a tree rooted at this vertex. And consistency here means that if you take two vertices, U and V, and you look at the tree of U, the tree rooted at U, and the tree rooted at V, and you look at the UV path in that tree and that tree, they're identical. Okay, it's a little strange, but I'll remove this mystery in a second. These two notions are essentially equivalent. So if I give you, whether I give you a path system or whether I give you a tree system, it's all one and the same. And simply in the proof, sometimes it's preferable to work with paths. Sometimes it's preferable to work with trees, and it's just a matter of convenience. How do you move from one concept to the other? Very simple. Let's say I give you a path system. What's the tree of corresponding to V? You take all the paths from V to the other vertices. You take their union. Why? So this is of course a spanning graph. Why is it a tree? Consistency. I mean, these are very simple things which I skip. I go over very quickly. But if you think about it for 2 minutes, you'll realize this is a tree. And the opposite is also very simple. I give you a tree system and you want to create a path system for it. So you want to know what is the path between U and V. Take the tree corresponding to U, take the path in this tree from U to V. That's the path UV. And you see that symmetry is maintained exactly because of the consistency property of tree system. Okay, let's come back. I very briefly said, yeah, if there are weights, then perhaps there is ties to break. But these are rather simple things. If you have a positive weight on the edges, then the shortest paths are uniquely defined. And what do you do with breaking ties? You can do whatever. I mean, very simple. For example, you can pick an ordering on the edges and break ties according to lexicographical ordering, something like this. So this is all very simple. But already the next thing shows you something interesting and a little unexpected, perhaps. There's also a very natural notion of a partial. A consistent partial path system, which means I just give you a collection of paths, and whenever this is relevant, the same condition holds. So that's a notion that makes a lot of sense. It also has been studied, but I won't go into this whole history. But so in this picture, you see such a collection. But let me stress that this cannot be completed, this cannot be extended to a full consistent system. Why? Look at this example and then ask yourself, well, okay, this is a consistent partial path system. How do I go from U to V? Let's say I go blue, red, red, okay? But that means this contradicts the first two steps. The instructions are to go orange twice. So however you go, you fail. So just having a partial doesn't necessarily extend to full. Okay. There's another very interesting point, which I think both Daniel and I think that this is an interesting issue, which we have decided one way, but we plan is going to continue with his PhD, so perhaps that would be our first project. What do you do with single edges? So if whenever U and V are neighbors, the path between them is this edge, such a thing is called a neighborly path system. And we decided not to insist on this. But in hindsight, once we are done with our first big project on this, which is that paper, by the way, it's on arXiv, you can find it there, and you're most welcome to read, comment, think about these things. There are tons of interesting open questions here. Perhaps assuming restricting the attention to neighborly systems is perhaps even more interesting, but that we haven't explored yet. That perhaps is the next project that we will do. So again, just to make sure we're all on the same page and you understand the most fundamental concept that we're discussing here, we have a graph, we have a consistent path system. The path system is metrizable, means that there is a weight function on the edges such that every path in the system is at least as good as any other path, and strictly means that it's better than any other path. The inequality is strict, and a graph is said to be metrizable if every consistent path system is metrizable, and strictly metrizable if every consistent path system is strictly metrizable. So perhaps this is a good spot to short for a very short break, just to make sure all really. In general, you're most encouraged to ask questions, make comments, tell jokes, whatever. But this may be a good spot to stop for a few seconds and encourage you to ask questions in case you have questions or comments. Okay, none. Okay, so I continue. So there's some very simple things, just again to emphasize and make sure you're all with me on the to prove non-metrizability. It suffices to show one consistent path system that's not metrizable. Okay, so it's for all other exists. So this is of the exist sort. As I said, we do not assume that the path systems are neighborly, and this may be an interesting thing to explore in the future. And we can, in the whole discussion, restrict ourselves to two connected graphs, because if you have a non-two connected graph, then really every path system is like here. There is something on the left and there is something on the right, and the connection between left and right always goes through Z. So it's very simple to see that there is really no loss of generality in restricting the discussion to two connected graphs. Okay, so of course, no mathematical lecture should go without a proof. I'm actually not even going to give you a proof, but I'm going to describe to you a nice proof. So we're proving that the theorem, I'm describing the proof. It's really not very technical or very difficult, and I'll be able to explain the ideas to you nicely in these slides. So we're proving the theorem in the title. Cycles are strictly metrizable, okay? Again, what does this mean? If you give me a consistent path system on a cycle, so, trees, we said they're of course not two connected. That's the minimal two connected graph, a cycle. So this is naturally the place to start. If you give me a consistent path system on it, then there are weights which generate this path system. Okay. And let me restrict myself for a moment. You'll see why to an odd cycle. In an odd cycle, the odd cycle is, it meets always from the beginning, from my first slide of being a geodetic graph, and then it's all very simple. In an odd cycle, if the edges are length 1, what you do is very clear. A different way of seeing this, and now you can see the concept of a tree. So you look at the C5 on the left with these pictures, among these pictures, and you understand really what happens. What is the tree corresponding to the red vertex? It's the cycle minus the red edge. Okay, so this is what I'm telling you things which are obvious, and what the theorem will say is that essentially this is all there is to it. So with a slight modification, which I'll learn momentarily, any consistent path system is such a thing, like this system in C5 with some slight modification. That's all. That's what the theorem says. And for this reason, cycles are strictly metrized. Okay, so again, if you have, so again, we're thinking about what is a path system on a cycle. So since you're at a vertex, you have to go somewhere. You have exactly two choices, going clockwise and counterclockwise. And so there is exactly one edge which you will never traverse. So a consistent path system on a cycle is essentially equivalent to a mapping from vertices to edges. So every vertex arrows or chooses the edge that it will never use. And when is such a thing, such a system of maps, when does this correspond to a consistent path system? Exactly when you have this crossing condition, that if you take two vertices, then either they both avoid the same edge, or the diagonal u comma fu and the diagonal v comma fv cross each other. And so the lemma says that such a mapping corresponds to a consistent path system if and only if it's crossing. And now that really, so now let's see what happens in the general case. No, not an odd cycle, the simple situation. The new additional ingredient that may appear that didn't appear there is this concept of a persistent edge. That look at the two yellow vertices on the top of the sixth cycle on the left. They're both mapped to the same edge, which means the white edge between them is never traversed. No one is using it, okay? And such an edge is called persistent. And what the claim, so these are non-trivial but not very difficult proofs, but they're non-trivial, they take work. That if you shrink such persistent edges, all of them, then eventually what you'll get, you'll come back to the situation of the odd cycle. That's the theorem. So again, if P is a neighborly path system, consistent path system on a cycle, and you look at all the persistent edges, and persistent is what we said before, then after contraction of these persistent edges, what you see is simply an odd cycle. And you can see now, so in other words, think of the colorful edges as having length 1, the white edges as having length epsilon, and then you simply follow. So what the theorem says is that when you've done this, the number of colorful edges is odd, and you simply go by the corresponding odd cycle, where the white edges are considered as being almost weightless. Okay, so that's how we prove that cycles are strictly metrizable. Okay, so now we want to understand a little bit more about metrizability. In fact, okay. Okay, so despite my very long experience in lecturing and so on, you can also imagine that it was Daniel who did the beautiful artwork in these slides. So about 20 minutes before I lectured, I hysterically called Daniel and said, "Can you create for me another slide, another slide, another slide?" And he did, and he actually put it in the right place. And stupidly, I put it in the wrong place. So let me quickly tell you, so he was right. Okay, here is, so now we want to understand metrizability. And one thing you could ask yourself, you know, we, by now, minors, we understand them reasonably, or some people understand them very well, but metrizable graphs are not, the class of metrizable graph is not closed under minor. Okay, and in fact, now it's a good time to explain two things which will come. This whole paper couldn't exist without very substantial use of the computer. Again, Daniel, not I. He wrote some computer programs. These searches, we couldn't possibly do them by hand. But the nice thing is that in hindsight, so we can verify them. Humans can verify the results the computer found, with one exception so far. The graph on the left is metrizable. The graph on the right is non-metrizable. So I told you proving non-metrizability is relatively easy. So again, there is some system, a linear program, blah, 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 everything runs. The graph on the left is metrizable. We only know because Daniel's program found it. And it's the one instance in these results that we don't know. We have to trust the computer. So if you don't trust computers, I think there are many things in life that you don't do. But anyway, it is not a minor closed family, okay? So now I come back well. Okay, so we want to understand metrizability. So minor closed is not okay.
Nati, does
Sure.
does it mean that for the graph on the left, the computer really goes through all these path systems and finds
exactly. No, it's almost shameful. You know, it's brute force. Nothing elegant or intelligent. You just brute force checks everything possible. I mean, it's a huge number. Therefore, we can only run it on small graphs. Okay, so let me return. Yeah, but this is the situation exactly. So, but topological minors, that's a different story. This is what I want to tell you next. So if a graph has a subgraph which is isomorphic to a subdivision of, okay, then we call it a topological minor. I hope you all know this. And the theorem says that the topological minor of a metrizable graph is metrizable. So the class of metrizable graphs is closed undertaking topological minor. It's not minor closed, but it's closed undertaking topological minors. And in particular, if a graph contains a subdivision of a non-metrizable graph, then the graph is non-metrizable. And here, this is the beautiful example which shows you how the sixth wheel on the left contains K4 as a topological subgraph. Okay. So I'm asking myself, let me only say, okay, I'm a little bit in trouble with the time, but let me just say, how do you prove this? These are technical, but not particularly difficult proofs. How do you prove this theorem that the topological minor of a metrizable graph is metrizable? Then you have to show that metrizability is maintained under edge removal and suppression of a degree 2 vertex. Edge removal is really very simple. Suppression of a degree 2 vertex takes more work. Somehow you have to, let me say, okay, I'll say just a few words. This is really, I don't think this is particularly useful, but I'll say just a few words. These proofs are not very difficult, but let me just to give you the impression, and then you're most welcome to read them in the paper. So what do? You want to show that vertex suppression doesn't foil metrizability. So you take a graph, you suppress a vertex of degree 2, you have a path system in the smaller graph in G prime. So first of all, you have to extend it somehow to a path system in G, but G is metrizable, so you have weights that realize it. And then you have to modify these weights somehow so that they work on also for G prime. That's very shallow, but at least you understand, what kind of steps are needed. Okay. Now let me. It's again, we're coming back again to the role of the computer in this work. So again, Daniel wrote a computer program that goes over graphs. You see, these graphs are not very big, and checks. It goes over all possible consistent path systems. With each one, you associate the linear program. If the linear program has no solution, bingo, you know that this is a non-metrizable graph. And he found this way these 10 graphs that you see here. Okay, but okay, that's a good, perhaps a good point to stress. I don't think we could possibly do this by hand. So this is not work for humans. However, once we know that this is non-metrizable, the program comes back with the path system, a consistent path system, and a linear program. And that can verify that this path system, for this path system, if you write the corresponding program, a linear program, it has no solution. Let me add one more word for those who are more familiar with this kind of thing. Even this is not, even this requires a little bit of theory. Why? Because in principle, you should compare, it's exponentially large, right? I mean, you chose some path and there could be exponentially many paths that connect these two vertices. But if you're familiar with the theory of Gretchen Lovas and Schreiber around the ellipsoid method, all you need is a membership and separation oracles. I'm talking now to those who know this kind of stuff. If you don't, then it will be over in a second. And if you don't, I highly recommend that you learn it because it's a beautiful and powerful theory. So using this theory of Gretchen Lovas and Schreiber, you can actually do this efficiently. And so we have, for each one of those graphs, we have a certificate that humans can check and see that these graphs are non-metrizable. So such certificate is comprised of two things. It's a consistent path system, which you can check. Consistency is very easy to check. And a system of inequalities that is, again, very easy to check because that's a path, the chosen path between these two vertices. That's a competing path connecting them, and you write that this is larger than or equal to those, and you combine these inequalities with non-negative coefficients, and you get the sum to zero, end of story. So again, while we were not able as humans to do this calculation, we are able as humans to verify that what the computer told us is true. Okay. Okay, so I mentioned to you that metrizability is rare, and how does this work? So now I went already a few times into this business of writing a linear program, showing that, and you saw this in action, but actually now we have already two distinct ways of proving that the graph is non-metrizable. One is what I said before, constructing an explicit path system and solving the linear program. The second, you could say, is a ready-made version of the same thing. We've done this once and for all for these 10 graphs, and if you find a subdivision of any one of them inside your graph, then that's a different way of proving this. And this indeed provides a way of, for example, again, showing that Petersen is non-metrizable. So if you erase these three white edges in this graph, you get one of the 10 graphs in that previous slide. Okay, so here's, I said that I'll be concrete about what I mean that metrizability is rare, and here's a theorem that says this very precisely. Skip for a second the first part, and let's go to the second one. A three-connected graph with 8 vertices or more is non-metrizable. A two-connected non-planar graph with 8 vertices or more is non-metrizable. A two-connected graph where all the degrees are at least 3 and has at least 13 vertices is non-metrizable. And how do you go about this? The actual proof uses these 10 graphs in a very substantial way. And somehow you're looking, of course, we can always restrict ourselves to two connected graphs. And it's enough that we find there a subdivision of one of these 10 graphs from before. That's the principle behind this. This is very technical, not easy, in some sense completely elementary. It doesn't use anything, but it's, it's hard work. It's like chopping books. Okay. Okay, so as I said, I'm returning to this this point again, that we have already two methods for proving non-metrizability. Proving metrizability is, again, for humans, for Daniel and for myself, much harder. We really have to sweat a lot, and we have a very limited tool set in order to do this. We still do not understand this at all. We understand this in a very shallow way. Okay, how do you prove it? So here is what seems like a very technical lemma, but it turned out to be extremely powerful and useful. So a path in a graph is called a suspended path if all the vertices other than the end vertices have degree 2. And what this theorem says, if you have a metrizable graph and you connect to the two end vertices of a suspended path, then this maintains metrizability. That's again very hard work. Again, I think I will skip it. It's a quite a long and technical. Let me say just a few words about this. No, I'll skip it. It's impossible to explain this thing on a slide. The general structure of the proof is not difficult at all, but it's quite technical and quite involved and takes quite a lot of work. So I will not even try to. So again, we are on our way to discuss establishing metrizability. So what follows from this theorem is that, so I promised you, when I said at the beginning, here are our main discoveries, I promised to you that we have an infinite family of non-trivial examples of metrizable graph, and this is the theorem. An outer planar graph is metrizable. What's an outer planar graph? Let me remind you, it's a planar graph which can be drawn in the plane in such a way that all the vertices are on the outer face. So all such graphs, so one example we saw, the cycle, but actually all the guys that we see here are like this. And why is it so? Again, because this business of suspended path. You can start with a cycle and connect pairs of vertices which are connected by a suspended path, and this way create all outer planar graphs. In this example we saw before. So now I want to speak about minors, topological minors. So the next thing so this shows you. So that's a second showing of this slide. I already did this before. I showed you this example with that metrizability is not, or metrizable, the metrizable graph is not minor closed. And remember, the thing which I said here is that this is one fact that we are not really relying on this, but we know this, but unfortunately, for this one, we don't have a humanly verifiable proof that the guy on the left is metrizable, whereas the guy on the right is non-metrizable. So minors is not the way to go. Topological minors is. Okay, so let me remind you a little bit. Again, I'm assuming that you've all heard this. I don't know how much at home you are with these things. Whenever you have it's really what I'm saying now, the stuff that I'm going to discuss now is really, if you want, it's much more general. It's about monotone Boolean functions, if you wish. So you have a family of objects in this case graph, and some operation that can take you up or down, and you're talking about something that's closed down, some ideal if you speak this language. That doesn't matter much. So whenever you have such a thing, membership is down-closed family is defined by its minimal non-members. This is completely general. And I want to discuss it under two circumstances, the situation with minors and the situation with topological minors. So what I'm saying here is this says it's much more, in more words, if you have a family that's minor closed, then membership is defined by it's the collection of minimal non-members in terms of minors. So in other words, this is all the graphs which are not in the family, but if you take any minor of them, then they fall into the family. That's how, and the big, of course, forbidden minors theorem of Robertson and Seymour, this mega result is that every minor closed family, for every minor closed family, this set of what I call gatekeepers is finite, okay? Every minor closed family is characterized by a finite set of forbidden minors, okay? As I said, initially there was nothing in particular that was particular to minor and so on. It was, as I said, much more general, just an ideal, something that's closed down. And how does this work with respect to topological minors? The first part works the same way. However, there is something very different here. So one way of stating the Robertson-Seymour theorem, and in fact, this is how it was formulated when it was generally known as Wagner's conjecture, is that there is no infinite antichain of graphs with respect to minors. If you have any family, any infinite family of graphs, then one would be a minor of another. This is not true with respect to topological minors. And here, I even made these things relevant to today's health situations. I call these graphs the corona graphs for reasons that are quite obvious. And this is an antichain. And none of these graphs is a topological minor of another. So you could ask, okay, so could it be that this foils the situation that we are unable? No, so let me go into the theorem. The family of strictly metrizable graphs is characterized by a finite set of forbidden topological minors, okay? And again, I remind you this business of suspended path. So the claim, which is really just repeating the same thing, if you have a minimal non-member and it contains a suspended path, then the ends cannot be connected to each other, because if they did, then by removing this edge, you would still be metrizable, contrary to the assumption that this is a minimal non-member. So now you can go back to this and ask, could it possibly be that this infinite antichain gives us trouble? No. If the guy on the left is one of these, it could not be one of those minimal elements, because the guy on the right is a subgraph of it, and therefore with this suspended path argument, it cannot be also a minimal member of. Okay, so right. So in fact, this theorem appears again. So Robertson and Seymour also proved that if I give you a graph, then in polynomial time you can decide whether or not a given graph G contains a subdivision of H. And now if you put everything together, then it follows that metrizability is polynomial time decidable. Why? You have this finite list of graphs, you apply Robertson and Seymour, and voila. But this is really, this is why people say that mathematicians are impractical. This says nothing. I mean, it says a lot. I'm very happy to include it as a result in the paper. But again, we really do not understand metrizability, okay? So it was a big surprise for me, at least, that metrizability is polynomial time decidable, but we still do not understand metrizability, whereas non-metrizability, we have a decent understanding. For metrizability is still very mysterious. So here are some open questions that we still don't know. So just to illustrate how little we know and how much there is still to investigate here, take the following class of very, very, again, I think I gave Daniel hell with this. He must have heard me asking this question 100 times. Can't we do the thetas? So what are the thetas? And we can't. The answer is no, we cannot do that, or we can do them partly, but we cannot do them, all of them. So what is a theta graph? It's a graph that has two vertices of degree 3, and they are connected by 3 paths of length A, B, and C. What is the status of this guy? Okay, if one of these A, B, C is 1, then that's easy. Then it's an outer planar graph, and we know it's metrizable. We also know that if A, B, and C are sufficiently large, 3, 3, 4, and above, then it's non-metrizable. And above follows from the theorems that, but for example, if one of these paths has length 2, then we don't know. And this is an illustration of how little we still understand about these things. So this is And it's not for lack of trying. It's not for lack of trying. It's not of lack of me nagging Daniel. We really tried it very hard. We still don't know. So, okay. So we know that there is a finite list of topological and minimum non-metrizable graphs. Of course, it would be very nice to know all of them. I don't know if there are 17 or 17 billion, no idea. We really have no technology at the moment at hand to resolve it. Again, an illustration of how much there is still to be understood it here. The third question I already discussed several times. Metrizability is still completely mysterious to us, so there is much to be understood here. The fourth one is also a point which I made. We really, both of us, believe that neighborly is a good assumption. So to develop an analogous theory where you want, you probably by now, some of you may have forgotten what neighborly means. Neighborly means that if U and V are neighbors, then the path between U and V is the edge U. That's a very interesting concept. Why? Think, for example, about the complete graph. So the complete graph is non-metrizable because deleting edges maintains non-metrizability, and of course it contains all the graphs. But if it's metrizable, if it's neighborly, then of course it's trivially true. I mean, you connect and there's nothing to do there. The situation is quite different. If you assume, so being neighborly is not just a technical thing that you may assume or not. It really changes the theory in a substantial way. And finally, the last question, which we haven't discussed much, but I think it's very interesting again for future investigation in this area. Yeah, it's becoming dark in Jerusalem. So the main observation or discoveries was that metrizability is rare. Is it even so? This is in the realm of all graphs, but is it also true when you restrict yourself to an individual graph? So take a graph, and there are two families of two notions of path systems that you can think of: consistent ones and those that are metrical, those that come from metric. So being non-metrizable means that pi strictly contains them. There are consistent path systems which are not metrizable. Is it true that in some appropriate sense? So this is a question that is still very soft. We haven't seriously considered it, but it's I think an interesting direction for thought. Is it true that typically there are many more consistent path systems than metric ones? And I think with this, yeah, I think that's a good spot to stop. And thank you very much.
Thank you, Nati. Thank you for a beautiful talk. Could I ask people to unmute themselves and give Nati a round of applause, should they so wish? So please just unmute yourself and go ahead with any question.
So Nati, this concept of metrizability is, I'm trying to get a grip on it here. On the one hand, you're allowing arbitrary weightings of edges, and it seems like a concept of this kind ought to not care about subdivided edges, and which your concept has authority in one direction only. In other words, so it's not quite a property of a topological graph.
Okay, good point, Peter. Thank you very much. It's really, I really think that this is the beginning of a whole jungle. in particular, you could think of the following thing, you know, think of a graph as a continuous one-dimensional complex. So an edge is really a path, is an interval. Very interesting. So the one place where we tried a little bit, but we didn't make, I mean, not it was so difficult, but we didn't progress. Well, the one place where we started thinking about a little bit about this, Daniel and I, was, I mean, you could ask the same thing, let's say, for the continuous cycle. And I don't know. I mean, there are various things that seem to translate immediately. Something seemed more difficult. I don't know, but I perfectly agree with you that these are, you know, these are very natural objects to consider. It's really, I mean, you know, I hope I was, you know, open and clear enough about this. We know what we know. I tried to tell you what it is that we know. There's so much more that we don't know and we'd like to know. And, you know, the more the merrier. If more people think about it, I'm very happy. Yeah, but what the point that you make is perfectly justified. Absolutely, I perfectly agree with you.
Well, it's fascinating stuff and a delightful talk. Thank you, Nati.
Thank you very much. Thank you very much. And yeah, I haven't seen you in a while, so it's very nice that good things. One of the few good things about Corona, right? Let me tell you something funny. I actually tomorrow, no, the day after tomorrow, I'm participating. I'm an examining guy in Tel Aviv. So there is the advisor and there is Irit Dinur and myself. And she wrote when we set the time, this is my social life now, you know. meeting people on exams on Zoom. What can you do?
So in many applications, you would probably from distances from a weight system on edges, you probably would want that it's, you know, the lightest weight versus the heaviest weight, they are within some ratio. So could you say anything? I mean,
no, I can't. But again, really, I mean, I hope I really gave you the sense that, you know, it's a free for all. It's a Wild West. You know, this is certainly an interesting concept to consider. You know, what happens if edge weights are bounded from above and from below? Does that make a big difference? No idea. No idea.
thanks.
You know, the business of neighborly, I think, is a good illustration. Somehow early on, we decided, yeah, we're not going to assume neighborliness. But at the end, we both concluded, Daniel and I, that this is worth investigating. And I think we will look into this. It's a different, I mean, I'm sure there is lots of common themes and so on, but it's not doing that same thing all over again. It's a different theory and would be very interesting. So many variations on the basic assumption are interesting and worthwhile looking into.
Thanks.